So there are two observables in which do not involve time explicitly are known not to commute. So there are two operators in which, well, if there was time dependency explicitly, we can write it like this, but it's not like this. So there is no time involved. And for that, we are saying that they don't commute. But there is a Hamiltonian of certain system for which this is true. They commute with Hamiltonian, but they do not commute with each other. So we need to prove that energy eigenstates are in general degenerate. Okay, so first we'll try to see that. So say there is A1 H is equals to 0. So based on that, let's say if I do this kind of operation H A1 N, this will, I can change the order because they commute. So this 0. And the Hamiltonian operates on a state which is here N is the and we have chosen it not to be degenerate. That's in the last it can be proved wrong. All right, we'll see. Since this is not degenerate, we will have some eigenvalue. Let's say that is En, which will be real since this is a Hermitian operator. So it seems that H A1 is giving us A1 times N. So A1 operated on N, this is an energy eigenstate. Right. Can look at it like this. Suppose that A1 when operated on N gives me something like this. So A1N, and when A2 operates in this state gives me when. But if A1 is not commuting with A2, well, case this can imply that A1 A2 is not equal to A2 A1. It is not true because A1 A2 are just certain numbers and they commute. So what is the other option that we have? Another option is this, that N must be degenerate. So what do we mean by degeneracy? That means that if I operate on A1 N, it gives me A1 N. But if I let's suppose A1 prime, yeah, this is for twofold degeneracy. Let's say if there is more, then this can go on, even double prime and so on. Similarly, we can say that n prime and so on. This so degeneracy basically means that state is same, but eigenvalues are different. So you can take multiple measurements on the state. You don't change the state, but still each time you get some different eigenvalues, right? Okay. So now can you try to look at this case? Let's say A2 will give me, let's say A2, and A1 on N will give me, let's say A1 prime, A2 N. And if I now change this, A1 can give me A1 double prime, A2 operated on this can give me, let's say, A2 triple prime, so on. So only in this case you can see that A1 and A2 do not commute. Why? Because you can say this is not zero. Only if all of this A1, A2 or double prime and whatever is, this is zero. If the energy eigenvalue, or not just the energy eigenvalue, the relative respective eigenvalue is zero, only then we can say this commute, but otherwise it is zero. They have also given us a Hamiltonian in which there is a radial potential. They have asked that Lz A1 Lx is A2. So this is a known relation for angular momentum, but Lz commutes with Hamiltonian. So does the Lx, because Z and Lx have theta phi dependence. Yeah, which is radial. So this is one of the examples. Now we are somewhat familiar with this kind of states where L is angular momentum quantum number, and M is written as magnetic quantum number, but like a component of angular momentum. So when we do this kind of thing, this Ly operates on M, we have this as not equals to 0, because there is 2L plus 1 fold degeneration. But if for L is equals to 0, it is what we call the S wave state. We say M is equals to 0, then doesn't matter what we write, all of them are 0. So this is an exception for angular momentum eigenstates.